Yes, we're probably gonna have to say, okay, we're gonna start recording in the room. All right, welcome everyone. I assume YouTube is rolling and welcome to the Zoom recording. I'm gonna go over here and click back on this thing. Should be good. All right, everyone, welcome to the Water, Wetlands and Watershed Seminar for fall 2025. This is our 52nd year. So we think it might be our either 103rd or 105th semester of wetland seminars, each with 10 to 12 speakers. So we're talking about thousands and thousands of opportunities for students and faculty here at the UF and abroad to learn about topics in water and wetlands. And starting in the COVID era, we started live streaming. So let's see, I've got a chat. It says that YouTube stream is good. Excellent. Okay, so welcome YouTube, everyone online. And we really opened it up and we've been able to have, viewership from all over the world, any time of day or night. And if you're ever can't sleep, you can go to our YouTube site and you can now look at pushing 100 YouTube recordings since the COVID era. But kicking it off this semester is Dr. Rafael Munoz-Carpena. I needed to print it out because we've gained so many accolades since we last were direct colleagues. But Rafa's #1 claim to fame. And then, can anyone guess? Well, he's got a couple, yeah. Oh, well, definitely from terms of citations, his #1 claim to fame probably would be VFSMOD or the whole Nash subclip efficiency thing. But he was also had the great pleasure of being my PhD advisor. So, and he's also a distinguished professor here at the University of Florida. And so Rafa's done work across disciplines. So he works with hydrologists and climate modelers, agriculture modelers, ecologists, political, regulatory folks, and really trying to solve questions about water quantity and water quality for societally relevant scales. And he's worked in the US and in Europe and in Central and South America, probably other places as well, also in Africa, looking at agricultural production there. And he's a very hardcore soil water physics scientist who also is able to zoom out and understand that the calculations and the expertise that he and his team bring are only relevant if they are combined with people that know how to grow crops and protect wetlands and, look for water for cities and people and be very conscious of climate and politics and all the rest. So learned a lot from Rafa, and hopefully you all will as well today. And with that, Rafa, here's the floor.
Thank you. Thank you very much.
We'll cut the light.
So a couple of things before I get started. This gentleman here confessed what he was doing his PhD, that he was not a modeler. All right, so here it is. Okay, so this is a little bit about modeling as well. And as I was discussing before, the context of this is regulatory policy, what is called regulatory science, for protection of surface waters, in particular the topic of pesticides. Okay, I'll give you a couple of numbers in a minute, but what we develop in models is also applicable in many other fields. Okay, so my core expertise is hydrological water quality, pollutant transport modeling, but I just came back a week ago from Bulgaria on a project we have with Ukraine, particularly to protect the infrastructure under continuous attack. So you might wonder why, but it's about resilience of critical infrastructure systems, which electrical communications and all these things are in Ukraine. So we can use a lot of what we learn in our biocomplex systems, okay, and then apply them to other types of systems. Okay, so we got a couple of new grants from NSF on this topic, and it's kind of interesting that we, what we learn really can be applied in many, many fields. Okay, so pesticides. How many of you are concerned about pesticides? All right, perfect. Why?
Because when you eat them, they can cause like different issues within your system and with other systems, and they can get into the water, they do all sorts of great havoc. They can reduce the immune system of certain animals, so that those animals are more susceptible to diseases.
Okay.
I think to me, just logically, if we're using some kind of chemical to kill something in an environment, then it's going to kill water for other life as well.
Unintended.
So we should not use pesticides?
No.
We should not.
No, we should.
Okay,
Why
why?
should not?
But-
Why? Well, let's look at the other side, because there is always a trade-off in everything, okay? So what's the story? Why are we using these potentially noxious chemicals?
Because they're very effective.
So if they're cost effective, it's hard to convince people away from that, and then it's just about applying it correctly.
Yeah, so I think the reality is that with the increase in population, the numbers we have today and the ones we'll have in the future, it's very hard to think about producing food for the quantity and quality we need without any kind of plant protection plans. Okay, we pretty much took the plants out of their native environments, and we put them under pressure, and we want them to produce and to secure that production, both in quality and quantity. Pesticides are part of it. Okay, I'm going to talk a little bit about that, but pesticides are not just released nilly-willy. Okay, there is a environmental framework, a policy framework that essentially is designed to the extent that is possible, in understanding all the complexities that a complex chemical out in the environment will have, is designed to get some degree of assurance that the chemical is not going to have unintended effects. Okay, and particularly in the context of the regulatory policies about the effects on non-target organisms. Okay, so you are targeting a particular organism, whatever it might be. It could be a plant, a weed. It could be a fungi. It could be a pest or disease. Could be any of those. And then at different times during the production cycle, it's important to control. Otherwise, the farmer would never get their crop. And all of us in the supermarkets will not have the food. Okay. So the regulatory policy framework, I will show a little bit about that in a minute. But just to give you an idea, the production of new active matters, new chemicals, okay, which is always or continuously developing, because these concerns about environmental impacts, new chemistries are coming along, new ways of modes of action are coming along. And there is, in general, there are two things that the regulatory framework, which is essentially risk analysis framework, looks at. One of them is what we call exposure, which means how does the chemical get to where it could produce, cause the effects. Okay, and the other side is what we call effects. So the exposure is all the pathways by which the chemical will move from wherever it's applied down to where we don't want it, which could be typically the aquatic environment, okay, an adjacent water body, for example, from the application side. The second part is effects, which is a biological response of the organism. It's a dose response type of relationship, whereas the non-target organism is exposed to that chemical, then it could have deleterious effects. Could be lethal, sublethal, and so on. Okay, so typically there are two parts of the environmental assessments that are carried out by both the registrants and the agencies that regulate this process. Okay, in the US is the Environmental Protection Agency that takes care of this process, and the registrants, which are typically the chemical companies and consultants that support them, have to produce lines of evidence, a lot of information to essentially prove that the chemical, under most of the conditions that are expected in the field, will not be noxious. Okay, now any idea how much money does it take to produce a chemical from synthesizing the molecule to putting it out into the market? An idea of ballpark cost these days?
Tens of millions.
Tens of millions.
A billion.
Okay, so it's about 100 in the cheap side to $400 million. Okay, time. Any idea of what's the timeline typically?
Isn't it 10 to 15 years?
Yes. And 40 to 50% of that cost is precisely the regulatory approval. Okay, so the synthesis, the packaging, the distribution, logistics, all those things only take about 50 to 60%. The rest is all the regulatory approval, which has many hoops that the chemicals have to go. It's called a tier system. So essentially you start comparing with water and you say, is it more or less, and say what? For sure not. Okay, and then you go up to the next tier. And as you increase the tier, you're increasing the description of the actual system, more refinement, we call it, okay? And then you're also getting closer and closer to what we expect to be the real effect, okay? So for most chemicals, you have to tier up the assessments, meaning that you have to add additional lines of evidence. So from simple indicators that you start on the lower tier, you now have to produce field trials, you have to produce laboratory essays on those responses. You have to produce modeling, which modeling becomes a very important part as you start going up in those tiers. Particularly the last tier in the US EPA is the third tier in European Union, which has a similar framework, similar models as the North America. It's step 4 is called. And in those, the final refinement, then they're looking at long-term effects of the chemicals. Okay, so not just a single event and what happens to the chemical, how it gets to the water, whatever, but also over a period. And they just updated the Environmental Protection Agency, EPA, updated the framework to 54 years of continuous data. And so there are around 300 agroecological scenarios, which are the intersection of locations, crops, soils, hydrology, time series, of all these things, which have been already measured on site, okay? And then that framework, which contains all these prescribed time series of rainfall, the soils, the rotation of crops for the particular location, all those things are prescribed, and then the registrant essentially comes with the chemistry, with the chemical characteristics of that, plugs it in, and then over time, over these 50 plus years of modeling, then we can assess what might be the concentrations in an adjacent water body, and from there, the risk to the effects on a biological non-target organism. Okay, that's kind of the overall framework. And so let me continue with this idea. Now, I started asking, about this issue of pesticides, and indeed it's a concern. It's a complex chemistry, very hard to really understand at the end of the day what's going to happen. There are more complicated things. Okay, we just started a project. We have a session actually on the next Water Institute symposium on PFAS. Okay, and that's really just the crazy of the crazy when we get into complex chemistry. Okay, then they have tallied about 20,000 different variants of that chemical. Okay, but nevertheless, pesticides are complex molecules, and although they are modified in the synthesis and production, they're modified to have some properties that we want them, that essentially make them less noxious. For example, we don't want them to move readily. So we make them to attach to surfaces and stay put. We want them to degrade fast. We don't want them to be around, creating problems, just whatever you need it, short time, do the work and get out. Okay, that's kind of the idea. So all these ideas have been around. There are also the idea of emulating nature, using some of the natural biocides that are in nature and trying to incorporate them in a useful way through different types of packaging and so on. So all these essentially, we are on the sustainable development goals. We have these four, among all the ones listed, these four in particular talk about water, food, soil, all the quality, environmental quality. And today, production of food, safe, abundant, of high quality, and not just the quantity, but also the nutritious quality of food is critical. And to really be able to do this today, we have to have plant protection products to do this. I mentioned that before. But the other side of the equation is that once we understand that these chemicals have to be in place, we also have to be looking at a framework for mitigation of these chemicals. Okay, and I'm going to be talking about mitigation on this talk a lot. So in other words, once I apply the chemical for whatever it is I'm trying to do, I also want to put barriers or lines of protection so the chemical doesn't end up where I don't want it, which typically is, as I said, an adjacent water body with whatever organisms that are there that could create damage. Remember that damage in population dynamics on ecology is about the trophic change, things that feed on things and then they accumulate, so there are chronic effects. They die because the concentration is too high immediately or soon enough, or they could just accumulate and then eventually produce a damage on the organism. Okay, so all these things are considered. So two key points is that we are to achieve the sustainable development goals is fortunately or unfortunately, we are going to have to use plant protection products. We're hoping that these products will be less and less noxious, but that's always a chance. And then also, in addition to the chemicals, when we use the chemicals and because we use the chemicals, we're going to have to use a lot of what we call mitigation practices, or in other language, best management practices to control those effects. Okay, so the problem with this essentially is how do you quantify the efficiency of these mitigation practices? And the problem is that it is a complex problem, okay? Because it's at the interface between the chemistry, these physicochemical properties of both the chemicals themselves, the soil, which ultimately is where they are applied on the surface, and then this chemistry and the soil properties determine in part the availability and the transport of these chemicals, but then also biological components, which essentially there are microorganisms involved. And then when we use vegetation as a mitigation practice, as I will explain in a minute, you have both the crop, which is biological component that affects the effect of these or the fate of these chemicals, but also if we use vegetation to protect, like I will explain in a minute, it's also a biological component. And then humans also are, of course, the central part of this complex system because they decide the land use. They decide the timing, the choice of crops, whatever the locations and so on. So all these interactions in different spatial, temporal scales ultimately determine that we have a lot of components which we don't really know what they are that determine how effective the chemical is going to be for a particular condition, and also if the mitigation practice that we might be applying might be effective or not, okay? All these components also, we don't know quite well the interactions. Again, the similar spatial temporal scales, processes, we don't know very well. So ultimately, what we get at times is, because we don't know the uncertainties that are embedded into the system, ultimately resulting in what we call, in complex systems, emergent behaviors, which means the surprises. Damn, it should not have happened. But all of a sudden we have this problem, okay? So, and that's because we really do not fully understand the system, okay? So uncertainty is embedded into these systems, okay? So how can we quantify the efficiency of a practice, a control, a mitigation practice, a BMP, to control the effect of these chemicals in the environment where we don't want them, okay? And then, just to give you an idea, there are many locations where the type of mitigation that we are talking about is vegetation. Okay, dense vegetation, I will explain in a minute, has the ability to control these chemicals. They could be placed, typically very seen as streams or lakes or reservoirs of different types. And they could be placed typically down the slope near this, but they could also be placed in the fields or up in the areas. Okay, just to control the runoff and the movement of the chemical before it gets into near the water body. Okay, there are other functions that have been assigned to these grass or buffer vegetation areas. Sometimes they are forests, sometimes they are typically we want a dense element of vegetation, but also deeper roots could be interesting for particular chemicals. But that mixture of vegetation typically could be implanted, sometimes it's natural, okay? The idea is that it could confer, in addition to the chemical protection to the water, it has other functions. So people have been looking at environmental corridors, okay? In an intensively cropped landscape, there are very few connectivity in the landscape. There is a lot of fragmentation, and sometimes this could be good for distributing species and maintaining them. But there are also effects of shade on the stream. Other things have been listed here. What we are going to be talking about is chemical protection for this, in particular for pesticides. Okay, so approaches that people have had in the context of regulatory policy. How do you use these products? So here is an idea. The products are being applied. There are frameworks to assess what the chemical impact could be on these non-target organisms. But then now we have a potential way to protect further, which is the use of this vegetation, okay? Now, how do you approach it? Well, the first approach would be what we call an empirical approach, which essentially is, are there any studies that have a look at these vegetation areas in the field? And then we measure before and after, the amount that chemical and water and everything that goes into the buffer, and then how much of that goes after. And then comparing the two of them, then I get an efficiency, okay? How much reduction I'm obtaining from that. So studies have been conducted where essentially measuring in and out, you can get some reductions. And then somebody comes along and does a literature review and synthesizes, and they say, okay, well, if we have a size which is, about 30 some feet width, all the way down to 60 perhaps, then we are gonna have this is reductions, expected reductions of 60% for runoff. But if we are looking at the sediment, we could have about 85%. But here is the number of studies that are based on these empirical factors or fixed factors that we call them are based on. Very limited. And of course, remember, experimentation is very important. Data, we need to gather realistic data. But the problem is that how do you generalize from the settings where these studies were made into other settings where understanding the complexities of the environment, different rainfall, different soils, different combinations of crops. So it's hard to really move from empirical studies into what might be all the cases that we might be interested later. Okay, so the first approach from a regulatory policy perspective is, okay, what's out there? Let's go and mine the literature and let's get some approximated reduction, expected reduction. And in this case, the table is length or size of the filter, from the edge of the water upwards into the field, to sizes, and then expected efficiencies for different types of constituents, water and steam. Okay. Now, as I said, the problem of fixed factors is that they are not really representative of a wider range of conditions outside the studies. However, they are very attractive because once you come up with these numbers, you can plug them in and say, okay, I calculate whatever chemical is coming, I multiply by 0.6, and then I get the number going down to the water if I have a buffer. But literally, the expected efficiency of any buffer, it doesn't matter what the size is literally from 0 to 100%. Okay? Why? Well, imagine a large storm where the buffer is totally overburdened, and basically the water is just flowing like, it was a pool, and then everything moves through. I mean, the vegetation there does absolutely nothing, okay? So that would be a 0% efficiency. Imagine a very, very small event where the water doesn't even run through because everything is infiltrated and nothing goes through. That's 100%. So the same buffer in the same location, depending on the variability of the precipitation, the runoff, the sediment on the source, and also the timing, because the rainfall could happen right after you apply, and then you have more chemical, So all these things determine really that the range of efficiency of these buffers is totally variable and very site dependent and condition dependent, okay? So these factors really do not capture that, all right? So our mantra, and here is a study, for example, my colleague, you'll see his name everywhere, I work a lot with him from Germany. So the idea is they did a literature review and they capture 200 and plus studies, and then they look at if the size of the buffer was a predictive quantity. In other words, how big the buffer from the edge of the water up into the field is. And then what you can find here is that there is yes, there is what you would expect, an upward trend. This is percentage reduction, 100% would be all the chemical is retained in the buffer, less than 0 would be nothing, okay? And across sizes, this is the size of the buffer. Well, the median sort of has an upward trend, which is what you would expect, a larger buffer maybe would protect more, but you can also see that the variability is huge and really there is not a very good prediction on the basis just of this. So what's clear is that something else, if the predictive variable is not the one that is controlling the phenomena you're interested on, there are other covariates that are affecting the problem, okay? And those are what you would expect, okay? Which are hydrology, sedimentology, and the pesticide characteristics, okay? Now, among the hydrology processes, infiltration in the buffer is one of the most important ones, sedimentation as well. I will explain to you in a minute, okay? But what's clear is that a simple solution based on the size, like these fixed factors, doesn't cut it. However, that has been used, okay, for the last 10, 15 years, because this was implemented in 2012. And then that was the only thing that people had were these empirical factors. When we came into the picture, I was actually called to a meeting in Brussels. They have been going for 10 years on the new pesticide directive, which is the highest norm in the European Union. These are the directives where all the countries have to abide to them. Essentially, the idea was that it was very aggressive. It was calling for 30% overall reduction of the pesticide use in the European Union and a delisting of about 30% of the active substances, okay? So, of course, the pushback was, well, the farmers were saying, well, how are we going to protect the crops? And, of course, the chemical industry wanted to sell their products. So, there was a lot of riffraff. And for 10 years, they were about, and how they were going to implement this directive. And one of the things that immediately came up on the surface was, of course, mitigation has to be part of the equation. Because if we are able to mitigate offsite, at the edge of the field, we might be able to use chemicals that otherwise they would not be allowed on the basis of the toxicity that they might have, okay? So this was sort of a preamble of the discussion to see what would be needed. Now, people, however, implemented because it's simple, the fixed factors, okay? And here is kind of a reflection of this, okay? So in regulatory approaches to essentially for any problem that has to do with risk, okay, are gonna be like the political design, one size fits all. I'm gonna come up with the size of these buffers and I'm gonna put it out there and I'm gonna expect that the reduction is gonna be great. Of course, what we understand is that that's not never gonna be the case, particularly in environmental matters. And then the next step would be this empirical approach based on studies, which is the fixed factor, some sizes fits all. And then at some point we realize that the sum is not enough and we need more ones. And therefore we introduce this concept, which is what we call quantitative mitigation, which is actually introducing all the processes, the dynamic processes that ultimately determine that, which is again, combination of the flow, sedimentation, chemical transfer, and all these things, okay? So that was what we put on the table. Now, up to this point, when we were introducing this topic, there were no models to really produce this type of description, okay? However, I had developed a model for this in my dissertation years and years ago. The model was there because my focus at the time was flow and sedimentation. So I was contacted by a couple of colleagues and they said, look, we came up with a way to predict the chemical reduction, but actually it's totally depending on the flow and sedimentation. Would you like to collaborate? And I said, sure, the model predicts that on these buffers. Then we put it together. If we put it together with the chemistry, then we'll come with a quantitative mitigation, or essentially process-based, mechanistic based prediction, where then we can incorporate all the nuances. effects of temperature, timing of application, all the questions that people have been asking. Now, this is the simplest one. So simplicity, okay, this is the simple one. And transparency, however, goes the other way. So when somebody in the dark room comes up with one solution and implements it, it might be simple. But of course, how did they come up with that solution, given that all these uncertainties are on the table, The next one, of course, would be this one, which increases a little bit transparency because we are the idea of the size matters, okay? And then the last one, of course, increases the most. But the problem with the last one is that it's also more complex and more difficult to explain. So there is always this trade-off between simplicity and the transparency towards decision-making in this context. Okay, so how do they work? Let's talk about them. Let's just take a very quick look at them. So we have essentially a production area. And by the way, this is now being used not only in agricultural spaces, it's used in urban spaces. There is a lot of landscape, which is maintained also with chemicals. And therefore, the same principles, so this as a source area, a potential water body beyond, and then some dense area, vegetation for protection. If it's designed properly and maintained, it could be effective in reducing chemicals moving into the urban waters as well, okay? Now, number one consumer of pesticides in the UK.
No idea.
Okay. Anybody? Yes? It's not agriculture. It's not advanced. What?
Lawn care?
No. Transportation links, railroads and roads, okay? So then again, these can be used for maintaining the vegetation around roads or in the railroads just to clean up and maintain them free of that. So there are many applications of this idea that have been put together. Okay, so how does everything start? Well, you have runoff coming from the field, you have the water body here, you put this dense vegetation, that's very important, okay, that is established, has time to mature, and then the first thing is that the overland flow, the movement, the velocity of water moving from the field, which typically has been compacted, is smoother, so the water comes at some velocity, but typically faster. Then it reaches the vegetation, which is very rough. And then the water slows down or stops, and then so the vegetation increases the hydraulic resistance to flow, and also the soil infiltration, if it has been established, the root systems, very dense, the organic matter that accumulates, okay, all these things eventually will improve the infiltration of the soil. Studies side by side in England, for example, where they have grasslands and then they put the grass buffer next to an adjacent field, they found that it could be in the one order of magnitude or higher infiltration in buffer compared to the agricultural field next site of the same soil. Okay, so the effect of this vegetation, because remember, these areas you cannot traffic on them. I mean, this is not a turning lane for tractors. The tractor has to turn here. This cannot be compacted. Okay, that's very important. All right, so under those conditions, then we increase the resistance to flow and the soil infiltration. And now, chemicals move in two phases, depending on their sorption characteristics. Okay, so they move as attached to the sediment. Okay, and that's a characteristic that is desirable in the design of these chemicals. We want them to attach to the soil. The problem is that the soil moves because there is erosion, and then when the soil moves, then the chemical goes. Okay, so they could be moved attached to the sediments when there is a runoff, and then they could be moved dissolved with the water. So depending on the distribution of that chemical between the solid and liquid phase, the two phases contribute to the transport, both as dissolved in runoff or attached to sediments when sediment moves. Okay, so how do these two effects apply to buffers? Well, the first one is that infiltration, high infiltration, reduces the dissolved phase because the water doesn't go directly into the water, it goes into the soil. Now, you might say, well, eventually it will make its way, but everything in chemistry, in environmental chemistry is about time, okay, timing. So you give additional opportunity for degradation processes. The problem is that runoff, the temporal scale of runoff is very, very short. So it's basically an instantaneous event where you move things into the water, okay? So you want to delay that as much as possible and then give opportunities for further degradation. So infiltration reduces the overland flow, the direct pollution, okay? And therefore the dissolved phase. And the mechanics of sedimentation, there is a branch of physics that deals with how these particles, the sediments move in water. The key factor is what we call transport capacity, which is the energy that the flow carries, okay, and it's a direct relationship with velocity. The faster the flow, the bigger the particles we can move all the way up to buses. Okay, you have seen that, okay, unfortunately, recently in Texas and other places. So that velocity matters. So the moment we decrease the velocity going through, the particles start settling. The coarser particles first, the finer particles, the last ones, okay, depending on the velocity. So the hydraulic resistance reduces the flow velocity, and therefore the sediment starts accumulating, the coarse sediment on the front, and then the finer sediment in the tail of the buffer. And therefore the salt chemical attaches and stops there as well. So the end result is that both the liquid and solid phases are reduced because of infiltration or because of sedimentation in the buffer. Okay, so depending on the chemical, we'll have that. Now, maybe an interesting story here is that, so how big does the buffer have to be to be? Well, it's gonna depend on what? On what? Well, what is this partitioning between dissolved and liquid, I mean dissolved and salt? In other words, how readily the chemical attaches and how much erosion and what is the size of the particles. So if the particles of the soil are coarse, they will be readily settled, and therefore if the chemical attaches to those particles and is mostly salt, so the characteristic of the chemical being soluble and the erosion of the particles being coarser, with a shorter filter, you are going to have a lot of efficiency because most of the sedimentation is about settling the coarse particles that come from the soil. And those are readily settled in the front of the filter. If the particles of the soil are very fine, okay, or the chemical is mostly dissolved, you're going to have a longer tail. So then the sizes of the buffers are going to depend on the chemistry, the source area, you know, all these things. Okay, you start getting an idea that this is not as simple as it looks. So ultimately, we need to watch the water, okay, infiltration, the pathways, the velocity is moving through, the sedimentation mechanics, the settling of these particles, and then the chemical distribution between the two of them to track the different phases and the reduction of them throughout the buffer, and ultimately the overall efficiency. So we get on one side the source area where we have both the flow, we also have the particles of different sizes, and then we have the distribution of the chemical and the solid phase. We have sedimentation process, and ultimately what comes out is the amount dissolved or in the sediment that goes through. Okay, so important to look at all these pieces in a dynamic way, because storm after storm, these things change. Okay, so it's very important to have a dynamic description and also process description. So this was my motto when I presented this in the World Congress of Chemistry in Australia years ago. You know, it was the chemistry. They were the UEPAC, the guys that came up with the norms to name molecules and things like that. Okay, and they had a branch on environmental chemistry, so they invited me about this, and then I started my presentation, which is not about just chemistry. Okay, but the fate, the transport, the things that we care about, you know, how the chemicals move along, ultimately, how much of the chemical gets into the water is really the story here. Okay, and to do that, we have to take this type of more complex approach, which again increases the transparency, but increases also the communication, the complexity. There are implications of that, which is that we've been working on this for 15 years with the regulatory agencies, and we just now are getting the tools deployed. You know, they're being used in regular assessments, you know, but it's a very long process to communicate this complex science. Okay, so people in marketing, you know, we need help. Okay, so
15 minutes.
okay, so let's leave it here. Okay. We developed a model which essentially has all these components. It's called VFSMOD, and it contains what we just described, you know, and there is a numerical model. So the overland flow is finite element solutions of the overland flow, sedimentation mechanics, and then we have chemistry, complex chemistry. We have a presence of shallow water table or deep soils without a constraining layer, like in the case of Florida in many places, because that affects infiltration and ultimately the partition between surface subsurface. And then in between events, that was during the event, and in between events, then we have all these processes, which is the mass balance, basically how much of the chemical is dissolved or short attaches or stays in the buffer, based on the partitioning of the chemical, based on the KOC or the organic carbon fraction. We have leaching in the soil, and then from the amount of the leaching, okay, so we have infiltration, we have leaching, and then we on the what is called the mixing layer, or the top layer, then we have the chemical that might be available to another event, and then we can also look at degradation between events, redistribution, remobilization, carryover, you know, a lot of processes ultimately determine in a continuous basis where is the chemistry, how it's going, how much it stays, and how much flows. Okay, So there is a lot of data as well, a lot of studies since 2007, the previous study I showed you. There was a revision of this work, about 300 individual tests with 35 pesticides, 57 countries. So there is a lot of data. You can see that the probability or the distribution of the pesticide reduction, which is on the y-axis, is that the percentiles, but typically you're gonna have more studies on the lower end and then less on the higher end, but there is enough distribution of efficiency to test models, okay? And also types of chemicals, this is KLC, which is sorption. So low sorption chemicals, more dissolved, and then higher on this side. So the database contains enough variability to test models on all these things, okay? The model was tested, the APA asked at one point, if we are gonna move into this world, where are the available models that are there? They tested a few, okay? And then, including ours, and then this is the error, okay? The small error, essentially for pesticide runoff and sediment, is the best solution, okay? So there was our model in all these assessments. And then, the model, all these assessments and the errors were significantly lower. And this was cold testing, meaning in the world of modeling, cold testing is you give teams data, you hide the results, they come back to the table, and then you show them the results and see how much is there, okay? So the physics are correct, we can get good prediction. This is a measure versus reduction across ranges. We can also incorporate effects of uniform, this is concentrated flow versus uniform flow, which are questions that have been asked. These areas are not nominally evenly spread. They could also have some meandering, and then we can incorporate that also, which of course the end result is that you have low efficiency. And we can also do a good job with the low sort and highly sort chemicals when comparing the results together. Okay, so how they are used in the regulatory context? Basically, in the higher tier, there is a field model that runs on a daily time step that takes care of the rotation of crops, the land use, the soil, the rainfall, all these things, and ultimately produces the sediment, the runoff, and the chemical distribution of that in the sediment and runoff at the edge of the field. Then it's taken into a water body model, which essentially does all the processes in a water column, which are sedimentation, there is some degradation, all these things in daily time steps. And then numerically, the model samples the concentration in water, and then it does a probability distribution of concentrations. And then it looks at some sort of upper percentile of that, typically 90th percentile, like it's put here, okay? So this will be all the concentrations that you obtain during the 54 years or whatever many years you want to run. This is the distribution of concentrations. You take a safe value, a conservative value, which is the highest 90th percentile, and then this constitutes the environmental concentration that you compare with the effects, basically those response studies that you do in the lab. If in this assessment, this concentration is greater than the lethal dose or whatever reference in the biological site is, then you don't pass the assessment, okay? So normally, the framework is field and water body. Our model then is incorporated in the middle, where the field is run through the buffer area, and then it fits back into this, and then the assessment is completed that way. So sort of this idea here. And then you can assess with and without the buffer what might be the reduction expected. And there are a number of tools developed over the years. This is one in California that we are working with quite a bit because it's very nice. Others are for consultants. Canada, for example, also has another tool. And we are now starting a big project in Brazil to incorporate these tools in Latin America. European Union has been ahead of the US, unfortunately, on this area because of all the latest rumbles with EPA and things like that. We have been delayed quite a bit, okay? There are a lot of guidance documents that we have put together. For example, this is a guidance document for parameterization in the context of North American scenarios. This is a big review paper that we did just a couple of years ago on this topic as well, and essentially all the aspects of regulatory policy and so on here. Okay, how long do we have?
10 minutes drop deadline, but if we have a few minutes for questions, that'd be great.
Well, it's up to you.
Okay.
Okay, so I had one question. We also did some documents for the European Union, long process of communicating, meeting with people. And I wanted to bring complexity in this, on many things that I already have told you about this process, but there are a couple of emerging topics that have been hitting recently and questions from regulatory agencies, because every time you introduce a new tool, there is always, without the tool, they were doing it very, very simple. Now you introduce the tool, and now big questions start coming up because you now start looking deep into processes, and then new things come along. So what happens to the pesticide once the event finishes? Does it stay put or does it go on to the next event? Part of the chemical could be remobilized towards the next event. The other one is this issue of multispecies, parents and metabolites. This is an interesting topic. Okay, I'm not gonna spend much time here because we did quite a bit of work on this. But the big story here is that in subsurface pollution, groundwater, things like that, there has been quite a bit of work into how a complex chemical could break down into metabolites and what might be the relative toxicity of the metabolites. Okay, and part of that is because the scale of degradation and the transport is usually slower or longer scales than what happens on the runoff. On runoff, because it's this hour-based type of event compared to days, months, or years, on the subsurface, then the belief has been that the opportunity for degradation on this on the surface might not be as important. Okay, however, that has never been tested. So that's what we said to do. Can we incorporate the mechanics to track not only a single product but all the chemicals? Okay, so that was the objective, to incorporate to design an algorithm, numerical, that is easy to implement, also portable, so that we can put it out there, and also is self-contained. So the big idea here is that we didn't want to rely on libraries, like some of you might be doing Pythons and things like that. We wanted to build everything in our code so that we didn't have to rely on external libraries. The reason for that is that regulatory models need to be certified. They have to be open source, they have to be understandable, everything that is there. So therefore, if we wanted to incorporate something like this, it had to be transparent and part of the code, okay? Which makes, makes the problem difficult because these are not simple problems. Okay, a couple of things just to give you an idea of how this works. We have the mass of the parent that breaks down into a product by a fraction, and then the rest of the parent essentially degrades and the product degrades as well, okay? So we can essentially say we are going to have a degradation, part of the chemical will degrade, okay? And then that degradation, okay, will be, which is a function, first order of the mass, is also affected by environmental factors, which are temperature and moisture. So your rate of degradation, the first order, okay, will be modulated daily by the temperature and the moisture content of the soil, okay? And this is a framework for degradation that we understand. So these two degradation rates, okay, will determine the speed at which the chemicals degrade, okay? And now we are going to have also another process, so they degrade this into this or this, the parent into this or this into this, but there is also a fraction, or essentially what we're going to call in the next step here, a rate of formation, okay? So the rate of formation is going to be the amount of the chemical, the parent, that doesn't go into the other degradation route, but actually moves into the product, okay? And that fraction, okay, which essentially the way to formalize it is based on the molecular weight, okay? And then you can actually obtain a rate of formation. So basically, at the end of the day, the change in mass for this product on the time step is equals to the rate of degradation minus the rate of formation, okay? So basically, how much you lose, how much you gain, for example, for this product in here. Okay, now for the parent, there is no formation, okay? So the formation rate is 0. But for the metabolite, is gaining from the parent, okay? And therefore you have another in there. So we can generalize these equations, okay? Incorporating essentially that the change in the mass for every time step is essentially the balance between what you degrade, the chemical degrades, and how much you receive from potentially other pathways, the metabolites, the parent metabolites type of relationships. This then can be generalized in a system of equations, one for each one of the products and metabolites involved, okay? This is the general form of that. And what's cool about this is that then you can write this as a system of equations, okay? This is essentially the derivative on the left-hand side. This is called eigenvalue problem. It's a mathematical thing that is well known, okay? But it is easy to then present any problem on the basis of this matrix here. Let me show you what that means. The solution to the eigenvalue problem is known in mathematics, but it's not trivial, okay? There is a lot of nuances on how to solve this problem because it depends on the structure of the matrix. So the matrix I presented before, how sparse, how organized it is, determines the solution method, okay? And there are libraries, huge libraries that have been developed to solve this problem. In Python, you just give the matrix and you give the initial value, and then it will spit out values directly, okay? You just call the library and it does it. But it's calling behind the scenes hundreds of different alternatives, analyzes the matrix, and then solves the problem, okay? So that becomes a problem because we cannot carry such a heavy weight on the solution, okay? So what we propose is solve the problem. Since it's a differential equation, we can solve it with essentially an approximation, a finite difference approximation, which is what we did. Now, what's more interesting here, and maybe that's the message, is that this matrix, actually using a network theory, can be put together to relate the chemicals. So let's take an example here. So we can take, for example, a couple products. We can take 3 products, a parent, and then 2 byproducts, which are related to some fractions, and then the rest goes out. Or we could be really crazy and start connecting products in so many different ways, okay? Now, what that means is that this matrix, what we call the adjacent matrix, which is essentially related to network theory, you can essentially populate parts of the matrix to establish the connections, okay? So for example, in this one, there is only one connection, I only have this factor. On this one, we have a couple of these, so I have 4 factors here. You see, the rest are not there because there is no reverse production. And then when you go crazy, you start populating selectively parts of the matrix, and then you can, in a flexible way, represent any kind of relationship between the parents and the metabolites. Just simply by choosing what elements are these are connections, and what is the rate of the transformation between those. And with this flexible framework, now you can put together a lot of different problems, okay? Now, we can also incorporate the effects of temperature, variable temperature, and moisture, okay? And therefore, for example, the black lines are without effect of temperature and moisture. This is the variation in this timeline, and this is with, so for example, it goes from here to here. You can see very distinct differences on the basis of these, the environmental factors influence, okay? So I had a case here to present. I can or cannot, I can stop here, but simply the take-home message is that I can take any problem like this, where, for example, I have a parent to metabolize, and then I can just run it through, and then now identify at the end of the day how much of the chemicals, these are the 3 chemicals, the parent and the metabolites, where in the soil they end up during the infiltration event, and then in between events, depending on the number of days. For example, here I have 11 days with a variable temperature and moisture content, and then I can estimate how much degradation each one of them is going to have, and ultimately, how does each one of the chemicals distribute, how much is at the end of the towards the next event, when the next event gets over, how much chemical is left on the mixing layer on the surface of the soil for transport and degradation. This has been implemented on the tools that are already part of the regulatory context, so that ultimately, for example, 54 years, 2,664 runoff events, where in between events there are so many days depending on what day it is. Then it calculates that the exposure concentration on the basis of all these events in the frequency that I presented, about 30% of the chemical is reduced for this particular event in California, for example, as we did here, okay? So that's it. We developed, among the many stories around the issue of mitigation and regulatory tools, this issue of the ability of incorporating byproducts is an emerging one. There hasn't been solutions provided for this. We incorporated an algorithm that we can use in the model, but also we can use elsewhere. Again, the PFAS story comes to mind. And then we can do it for the first time, and in fact, we can get effective answers. The next step is to test it against data. Okay, we have some reduced data sets for this, and it's part of the paper that we hope to finish in a month or so. Okay,
Awesome.
So
Thank you, Rafa.
that's it.
Yeah.
A couple things. Almost are wrong, some are useful. No? Those of you in class now understand this very well. Remember the Geiger rule? Garbage in, garbage out, perfect. And then also the story of Dimming and Box, okay? So Box, a statistician, I think it was Harvard or somewhere like that, stole almost around some are useful. His friend Dimming, who's working in the patent's office, a small rat, and he basically, they were good friends, and this guy took it out and made it famous, but he stole it, okay? All right, so here's the story. Okay, so thank you.
Rafa. We'll take some questions from the room. If you have to run to your next class, that's fine, but please stay if you can for 5 or so minutes of questions. And we'll take a question from students first, which is always a challenge, but we will wait for it. So students, question for Rafa.
Yes, please.
I have a dumb question, but it was something I was thinking about. What exactly is the barrier or like the border that you were talking about? Like you talked a lot about like that. Is that like just like soil in the way? Is that like, I don't know, blow up thing in the way? Like, I didn't really understand that. It's just grass? Oh. that makes
So
sense.
mix, because they are not grass in the nominal way, they are not granules, they are a mixture of legumes and graminants, typically to maintain vigor throughout as long as long as you can in the field. Okay, so they sort of maintain vegetation close, densely. They have to be mowed to maintain them closely, otherwise they just, what happens here in Florida in a couple of days.
Mhm.
So you have to maintain them as well. Okay. Yeah.
Thank you.
Everyone, yeah?
I haven't taken a lot of agriculture classes, but one thing that interested me is like. When you talk about like factories and stuff like that, oftentimes the wastewater they produce is. Then just like funneled back to a treatment facility. Is that just like not realistic in agriculture because it's such a wide area, like how realistic to try and funnel some of that, polluted water and then like treat it versus it kind of just disperse.
So I mean, treatment is part of the equation and there has to be a plan for treating excess. For example, if you're talking about PFOS or concentrated animal operations, that you have a lot of waste, you have to treat it, okay? Typically it's applied to fields, understanding that there might be a buffering capacity of the field, but if you don't do it right, or there is rain or whatever, you might run into trouble. But for example, in the context of pathogens from PFOS, buffers are starting to be used as a treatment option. Okay, so once you collect the water in whatever system you have, you run it through the buffers and then the runoff is supposed to be cleaner than whatever was going to be from the air. For example,
More broadly, yeah, I mean, there's this idea of point source pollution, like at the tail of a factory, you can just collect it and treat it. Then there's non-point source pollution, like from all the lawns and all the parking lots and the thousands of acres of fields they're so diffuse in space that is very few operation systems that you can collect it.
Right.
Things like concentrated animal or dairy operations are small enough that you can collect enough wastewater to make it worth it. But in a huge field, if you drive through north of here, yeah, how do you get it? Right, that's the
it
challenge.
should be maybe interesting that in North Carolina, the DOT developed the design of this median in the roads. It actually has buffering capacity, so it was developed with the model to essentially identify what might be the composition and size of those vegetation, so that the chemicals that wash off from the tarmac, they don't get into the point sources where they are run typically to your lagoon, near the road and so on. So there is a treatment in that right on site through the vegetation on the side.
And so for those really toxic chemicals, like not just like nitrates and phosphates and stuff, does buffering mean that that chemical is absorbed and processed somehow and then no longer toxic, or does it mean that that little buffer is just capable of kind of retaining that?
Good question.
But yeah, it's a very good question. It's the chemistry, okay? Most of these chemicals are designed to be labile. I mean, they are long persistence chemicals like DDT used to be are no longer in the market. They are not allowed. Okay, so you have to give time for the chemicals to degrade. So degradation is what happens. They break down either through microbiological activity, sunlight, all kinds of temperature changes, so they are depending on the chemistry of the chemical. But the idea is that they will degrade. They will break down into pieces. Hopefully, the pieces, the metabolites, are not as toxic as the particle. But sometimes it's not the case. Sometimes the degradants are more toxic than particles.
All right, maybe one more question?
Yes, so for those there's a slide where you're showing the different degradation models, like, is that based off of like a particular chemical that you were looking at, or it's just like a model chemical?
Yeah, in pesticide chemistry, first order, maybe higher order decay, depending on the cases, is the typical way to describe these chemicals. Now, there is a lot more going on there, but essentially all the factors of degradation, okay, are typically microbiological because they are big molecules and typical organisms cut them out. They are embedded into the first order decay equation. There are higher orders that can be put into here, okay, but what they have done instead is put in the first order and the modifiers for temperature, moisture that I presented there. So every day, you change the moisture and the temperature, and then you modulate the rate of degradation on the basis of those. So it's all based and is for all chemicals, for pesticides, okay, in particular. So that's kind of what has been adopted in the rotary context.
Gotcha, thank you. And is that degradation modeled like spatially or temporally or both, or?
So the model is spatial explicit, so it basically takes from the edge of the field, which is here, all the way down to the water, which should be down somewhere in here, okay? And then it takes, it's a finite element mesh, so it takes actually points separated whatever distance you want along. And then you can incorporate variability of the grass density, many other things. Now, in the regulatory context, that's not, they use a uniform section, okay, with all the properties along being the same, because the regulatory scenarios are very abstracted. You cannot really get into the nuance of a particular buffer here. What you do is you say, okay, in general, we're gonna expect this type of condition, and that's really an abstraction, okay? So the nuances of spatial variability are not really suitable for a regulatory scenario. Things are much more, typical. When you go into evaluating specific buffers, which the model can be used for evaluation, then you can incorporate this spatial variability of the buffer along, okay?
Thank you.
All right, let's give Dr. Munoz-Capena one last round of applause. Thank you everyone online. So,
Guys.
I always forget to do this. Next week, our speaker is, does anybody know? The big surprise it's going to be, Kamalpreet Singh. He's a PhD candidate here in the Department of Environmental Engineering Sciences. He's going to talk about from reactive to proactive public health, mapping coastal vibriosis risk with satellite data. So this is this flesh-eating, so-called flesh-eating bacteria that is basically causing havoc on Florida's coastlines. And we're going to talk a little bit about how to predict it and monitor it. So